Hi, in this video we are going to see the time shift property of the Fourier transform. Now we remember that the Fourier transform is a measure of the frequency content of the signal. That means how much e to j omega t is contained in the signal. So in time domain, a time shift will correspond to a phase shift in frequency domain. Now let us see the details of this discussion. Now let us consider the Fourier transform pair x of t and its Fourier transform x of omega. We claim the following, then x of t minus t0 will have the Fourier transform x of omega e to minus j omega t0. Here t0 is a constant. Is a real valued constant. Now, this is the time shift property of the Fourier transform. So let us now prove this result. Fourier transform of x of t minus t0 can be written as, in terms of the Fourier integral, the integral of x of t minus t0 e to minus j omega t integrated with respect to t. Okay, so all we have to do is change the variable to another variable. Let t prime be t minus t0. So this integral becomes x of t prime e to minus j omega. Now t prime is equal to t minus t0, so t is equal to t prime plus t0. So the differential element dt prime is equal to dt, so we have dt prime, and when t tends to infinity or minus infinity or plus infinity, t prime also tends to minus infinity and plus infinity, so we have the same integration limits here. So we have now e to minus j omega t0 is a constant term which can be taken outside the integral. So from minus infinity to plus infinity, x of t prime e to minus j omega t prime integrated with respect to t prime. But you see, this is nothing but the Fourier transform, x of omega. So this is the simple proof of the expression for the Fourier transform of the time-shifted version of x of t. So let us start with a very simple but important example. Example 1. X of t is the shifted impulse, delta of t minus t0. So Fourier transform of, okay, we remember the following. Fourier transform of the impulse is 1. Remember how we interpret this result. The impulse is a singular function which is 0 everywhere except t equal to 0 where it is infinite. So in order to account for this singularity, all frequency components, even infinitely high frequency components are represented with equal weight. And Fourier transform of x of t is therefore, by using the result we have just proved, e2 minus j omega t0. So this means that the magnitude of the Fourier transform is essentially unchanged because magnitude of e2 minus j omega t0 is equal to 1. But for each frequency omega, we have the corresponding phase shift of amount minus omega t0. Okay, now another example. Now in this example, we are going to use both the time shift property and the linearity property in this second example. Let us consider the following signal. X of t is equal to 1 for t between 0 and 1. And 2 for t, okay, 2 for t between 1 and 2, and 0 otherwise. Now, since we are going to calculate the Fourier transform of x of t, in fact, it is not important what the value of the signal is at single points like 1 or 2. You may put an equality here, for example, and maybe here as well. But without those equalities, we are also okay. I mean, since the Fourier transform is an integral, and since the value of the signal is considered at a single point, that value is of course not important in the evaluation of the integral. Okay. So graphically, x of t is from 0 up to 1, it is equal to 1. And from 1 to 2, it is equal to 2. And outside, and for all other values, we have 0. Now, at this point, we have to remember the signal rect t, which is the rectangular pulse. So, now remember that Fourier transform of rect t is sinc omega over 2 pi. Okay, we have the well-known Fourier transform pair, the Fourier transform of the rectangular pulse, which is equal to 1 between t between minus 1/2 and 1/2, is sinc of omega over 2 pi. So here rect is the following signal. It is equal to 1 between minus 1/2 and 1/2. Okay. Now, how can we express x of t in terms of the rectangular pulse signal, rect t? Now, it seems that we will be able to represent x of t in terms of a linear combination of time-shifted versions of rect t as follows. X of t is, now consider the part between 0 and 1. It is in fact rect t shifted by 1 over 2. So we have rect of t minus 1 over 2. Okay? And then, and the magnitude is equal to 1, so we have no change in the magnitude, plus, now the values of x of t between 1 and 2 can be expressed as 2 times, because the magnitude is equal to 2 rect of t minus, now the amount of shift is 3 over 2. Okay? So, by using linearity and time shift, and time shift properties, x of omega can be written as follows. Fourier transform of rect of t is sinc omega over 2 pi. So we have sinc omega over 2 pi, but we have also a time shift, therefore it is e to minus j omega. The amount of time shift is 1/2. Plus 2 times sinc omega over 2 pi, and the amount of time shift is 3 over 2, so we have e to minus j omega 3 over 2. So we are able to calculate the Fourier transform of x of t by using linearity and time shift property. How did we do that? We have expressed x of t as time-shifted versions, as a superposition of time-shifted versions of rect t. So in fact, one can just invent several such signals, which are superpositions of shifted versions of the rect signal, and even in a case containing many such shifted versions of rect t, we will be able to calculate the Fourier transform rather easily by using linearity and the time shift property. Okay, thanks for watching.